Okay, we're going to talk about now polyprotic acids. Now, some students find this quite confusing, and I just want to tell you up front that this is really not difficult. It is just adding an additional step to what we've already done, and there's nothing really new being presented here. So, as I've said before, monoprotic acids are acids that donate one ionizable hydrogen ion in each molecule. And so there's one available hydrogen or proton that can be donated. A polyprotic acid, or here's an example, this is acetic acid, there's only one ionizable or donatable, if you will, hydrogen ion or proton that can be donated. Diprotic acids are acids that contain two hydrogen ions or two protons with each molecule. And then polyprotic would be anything above one, actually. So diprotic is a subclass of polyprotic. And what happens is that you have what's known as a stepwise ionization. So you remove the first ionizable product, and that has its own equilibrium constant. Then you remove the second ionizable hydrogen or proton, and that has its own ionizable product. Okay, so one such diprotic acid is carbonic acid. And carbonic acid or carbonated water is produced by dissolving carbon dioxide in water. The solution that results is acidic because the carbonic acid that is formed. Now, let's take a look at how we would go about measuring the hydrogen ion concentration, the carbonate concentration, and the bicarbonate concentration and the carbonate concentration if we have a 0.33 molar carbonic acid solution. Again, here are the two reactions. So the first reaction that occurs is the carbonic acid donates a proton to water to form hydronium ion plus bicarbonate. Then the bicarbonate donates a proton to water to form hydronium ion plus carbon dioxide or carbonate ion. And you see that the first ionization has a Ka of 4.3 times 10 to the minus 7. The second has a Ka of 4.7 times 10 to the minus 11. So the first one ionizes more completely than the second. The approach is to do two steps. The first step is to find the hydronium ion concentration and the bicarbonate ion concentration from carbonic acid using the first Ka. Then, using the second Ka, you find the carbonate concentration from the bicarbonate concentration that you got from the first step. So you determine the direction, and you do this the same way, you just do it in two steps as opposed to one. So let's take a look at this very problem. So the first step is the carbonic acid plus water forms the bicarbonate ion plus the hydronium ion. The equilibrium constant for this is H3O plus divided by the bicarbonate minus divided by the H2CO3 concentration. And the Ka for this one is 4.3 times 10 to the minus 7. So we know that this is 0.33 to start, 0.033, excuse me. This is the initial, this is 0, this is 0. The change here is going to be x, and minus x. And so we're going to have 0.033 minus x at equilibrium, and x at equilibrium. So that x squared over 0.033 minus x is going to equal 4.3 times 10 to the minus 7. 10 to the minus 7 is a very small number compared to this, so we can drop this, and we can say that x, we can multiply both sides by 0.33, and then take the square root, and we have an answer of 1.19 times 10 to the minus 4 molar. Now that means the concentration of the hydrogen ion here is 1.19 times 10 to the minus 4, and the concentration of the bicarbonate ion is 1.19 times 10 to the minus 4. So we're going to save that number right there. And we're going to look at the second step, which is the bicarbonate plus water goes to form carbonate ion plus hydronium ion. And we have a second Ka, which is 4.7 times 10 to the minus 11. Now for this one, we know that this concentration is 1.19 times 10 to the minus 4. This is going to be x. And we know that this is 1.19 times 10 to the minus 4. That's the initial. Remember, that's the initial. This is 0. The change here is going to be plus x minus x. And so you end up with 1.19 times 10 to the minus 4 minus x, and 1.19 times 10 to the minus 4 plus x. So that you end up with x times x plus 1.19 times 10 to the minus 4. And that's divided by 1.19 times 10 to the minus 4 minus x. And again, this is going to be, even though this is 10 to the minus 4, it's compared to a number that's exceedingly small, 10 to the minus 11. So we can eliminate this x, and essentially this is going to be, leave you with x is equal to 4.7 times 10 to the minus 11 molar. So that's the carbonate concentration. So the carbonate concentration is this, and the hydronium ion concentration is this, and the bicarbonate concentration is also this. So that was the three questions. And then if you wanted a pH, you could put this number into your calculator, and you're going to get a 3 point something if you were to do that. But I'm not going to do that right now. And so anyway, the answer is 1.19 times 10 to the minus 4 for the hydronium ion concentration and the bicarbonate concentration, and 4.7 times 10 to the minus 11 for the carbonate concentration. Let's shift over and talk about buffers. Buffers are exceedingly important, and buffers are important in biological systems, and they are also important in other systems. And what a buffer is a mixture of a weak acid and its conjugate base, and the purpose of a buffer is to resist changes in pH. So on the right here, you have a buffered solution, or excuse me, on the left, you have a buffered solution and an unbuffered solution on the right. So if you take picture A, you have one of those is unbuffered on the left and a buffered solution on the right, and you add the same amount of a substance to change the pH. It has an indicator, methyl orange, that indicates the pH being 8. Now on the picture of B, you've added only 1 milliliter of a strong acid, 0.1 molar hydrochloric acid. And what you can see is that when you have an unbuffered solution, that this is exceedingly affected by this introduction of this very small amount of acid. On the other hand, the buffered solution does not change at all and stays the same. The buffered solution stays at a pH of 8. The unbuffered solution changes to a pH based on the color of the methyl orange of about 4. So here's how buffers work. You're starting out with the situation in the middle. You have a weak acid, which is, in this case, acetic acid, and its conjugate base, which is the acetate ion. If you add hydronium ion, what ends up happening is a shift of the reaction, as it's shown, to the left. And this shifts, based on Le Chatelier's principle, this shifts it to the left and forms a little extra unionized acetic acid. And so that essentially what occurs is the hydronium ion you've added is absorbed into an unionized formation of acetic acid, which can slowly dissipate over a period of time. Conversely, if you add base, it shifts the whole reaction to the right and you form extra acetate ion. And again, the addition of the base causes the reaction to shift to the right this time, and formation of more acetate ion, which again slowly dissipates. So the addition of an acid causes a shift to the left, and it removes that hydronium ion from the being present, preserving the pH. Again, adding base again removes that base by accumulating extra acetate ion. So buffers are exceedingly important in terms of being able to absorb the introduction of acid. Human buffer system is the carbonic acid bicarbonate system. And the way that we remove the acid is when we breathe out the carbon dioxide that's ultimately formed in that two-step process. This functions to keep our pH very, very, very tightly controlled.